the depth here is a 500. D effective here is actually from the concrete surface to the reinforcement, but there's no reinforcement here, but it stated the effective depth here is a 500. Alright, so FCK for the concrete, FYK for the steel, and then D prime, which is the locations for the compression reinforcement. So that means might be once you determines the types of this beam, either singular or doubly, if you get the results of doubly, this is will be the D prime here, the D effective for the compressions reinforcements, while D here is the depth effective for the tensions reinforcement. Okay, the same procedure. Same goes for the rectangles for the singular beams here, which is you need to compare with M balance. This is equation for the M balance. Remember, if M for the moment, for the design moment less than M balance, this is the M balance equations. Okay, so you can just design as a single reinforcement, just provide tensions reinforcements. So if moment more than M balance, then you have to provide both top and bottom, which is tensile reinforcements and also compressions reinforcement AS prime. Yang semalam duk tanya singular doubles, tak ingat kan? So hopefully you have idea, okay, for class for this morning about singular and doubles. So in this case, moment here is a 450, right? 450. You need to compare with the M balance. M balance dapat 260. That means moment here 450 more than the M balance here, more than the beams that consist of FCK 25. This is the dimensions for these beams. Okay, so M balance, that means it from the FCK, contribution from the FCK and contribution from the size of the beams that is given here. So that means M more than the M balance. So that means you need to design, provide the beam with compression reinforcement. So you need to have AS and also AS prime. This is equation for AS prime. Just replace, substitute all the informations for the M, all the value for the M, and also M balance, which is 260. M450, and then once you have to design as a compression reinforcement, it should have a D prime also. It also given here, guna je lah teruskan, so masukkan dalam nilai. You'll get AS prime is a 966. So 966 in area. Okay, power of 2 here. So how many numbers of reinforcement should be equivalent to the 966? What the diameter? So you need to refer to the table for the area of reinforcement. So this is AS here is a, I can say this is as a AS required. Okay. This is AS required. Remember, once you provide AS provided, it should be more or equal to AS required. Okay, so you should provide the numbers of reinforcement and the suitable diameter according to AS required. Okay, from the tables. Table dah tunjuk last week kan. Okay, so because we have compression reinforcement, you need to do the checking. So this is the checking for the compression reinforcement. It should be D prime divided by S should be less than 0.38. Okay, so kalau you if less than it, that means compression still achieve its design strength at 0.87 FYK. Okay, so kalau checking untuk tension reinforcement, ingat tak berapa? D divided by X, it should be less than, anyone for tension checking? 0.45. Okay, so this is for compression, this is for the tensions. Why we need to do the checking? Because we want to ensure that the sections, the beam is under reinforced. Once it under reinforced, that means all the reinforcement, all the steel reinforcement achieve the yielding strength, achieve the yield point, achieve the design strength of 0.87 FYK. Okay, so then we have a AS prime, and also you need to determine AS. Okay, so this is the equation, just replace it. So this is all the reinforcement that is need to provide, that we call it AS provide according to the AS required. This is all the AS required. Yeah. Area yang diperlukan, dan ini adalah reinforcement area yang disediakan. Okay, according to the AS required. It should be equal or might be more than it. Kalau more than AS required pun mestilah reasonable. Ni sebab melibatkan cost juga kan. So janganlah terlebih-lebih sangat, terkurang pun tak boleh, should be just nice. Okay, so then we have a compression and tension reinforcement. How to draw it? So compression reinforcement 2H25, so that means there are two bars with the diameter of 25. This is the diameter, so you will have to note that here 2H25. Then for tension 5H25, how to arrange? Macam mana nak susun? So it should be mirror lah. Okay, so let's say this arrangement, which is 5H25. So this will be D prime, which is center to the compression bar, D prime. While for D, effective depth for the tension, kalau ada dua layer, it should be at the middle here. It should be in between the bars. Okay, so this is the effective depth for the tension, this is effective depth for the compression. For example number 2, so in this style, it gives a section that consists all the reinforcement with the dimensions, with the size of the bar, with the size of the beam here. So from this section with all the reinforcement provided, you need to calculate what's the capacity for this beam, what's the moment resistance for this beam. Okay, maksudnya you kena reverse balik calculation. Dia bagi 3H20, so what's the area? What is AS provide according to these numbers, according to this diameter of bar. Tengok table 3H20, berapa AS provided? Sama juga ni 5H25, AS provide. So AS provide berapa? Tengok table. Okay. Then you have to understand of this stress block diagram also. Okay, so because of compression reinforcement, kita punya internal forces bertambah. Okay, so ada FCC for the force concrete in compression, then we have FSC according to the steel in compressions here. Okay, it should be level with the positions of compression reinforcement. And we have another one, FST, which is force for steel in tension. So this one should be also equivalence positions with the steel in tension. So we have three these all internal forces. So this is AS provided according to numbers of reinforcements in the beam sections. Okay, you can come out this area, refer the tables. Okay, then we need to do the checking. So as x divided by d and also d prime divided by x. Okay, yang ni tadi terbalik tadi ni terbalik. Should be x divided by d. Okay, you need to do the checking. Sebab the reinforcement kan, kena buat checking. Sama ada still to achieve the design strength or not. Okay. This is checking. Number one, x divided by d, compare with 0.45, checking for tension reinforcement. D prime divided by x, checking for compression reinforcement. So dalam checking ada x. So that means you need to find out what's the x value. What is the x value, which is the neutral axis depth, right? Okay, which is this one is from the diagram. Okay, I will not repeat back how to define these equations. Okay, so it shows here that all the reinforcement, all the steel reinforcement achieve design strength. So that means you can proceed. Kalau tak achieve, which is more than it, you must do something. For example, increase the size of the beams. Let's say change the D or change the D primes. Okay, if you increase the size, okay, the D and also the D prime also will follow the changes. Okay, mungkin size yang you propose sebelum ni tak cukup. Okay, it's not sufficient enough to ensure that you still achieve the design strength. So you need to increase the size. Kalau sebelum ni lebar 200, so you tambah mungkin 250. Okay, kalau depth 200, mungkin tambah jadi 300. So you will see the changes of the value. Okay, so moment resistance. So this is the main questions. Okay, right? So you need to determine the moment resistance for the beam section. This is from the FCCZ, FSCZ1, which is you make a moment at this point, right? So that means you calculate what is the moment at this point by multiplying all the moments from FCC and FSC. FCC multiply with the depth here to this point. So and also FSC darab dengan Z1, FCC darab dengan Z. Okay, dapatkan moment pada point still. Okay, so that is how these equations obtained here. Okay, so substitutes all the value here. Okay, then this is the moment resistance for the beam, which is 462. That means this beam, okay, this beam have a capacity of moment resistance up to 462 kilonewtons meter. Dia boleh carry these loadings, okay, up to 462 kilonewtons meter. Alright, so that's it. Any questions before I go to flange? Any questions? Ada soalan? Okay, faham Okay, then we go to flange beam here. Flange beam. So kalau semalam siapa datang, I ambil peluang juga untuk terangkan kan. Flange beam can be two types, right? T-beam and also L-beam. Semalam group yang datang terangkan juga dekat you punya group member Okay, so flange beam, it can be L-beam, it can be T-beams as long as the beam continuous or cast together, concrete together with the slab. So then dia akan jadi flange beam. So L-beam, it should be at the corner. Okay, T-beam, normally it will be for the internal beam. So that's why dia jadi T-beams. Okay, let's say for this line of the beams. Okay, kalau buat sini dia akan jadi L-beam. So this is the slab, this is the beam, this is the slab, this is another beam, slabs, and this is the beam. So that's why kalau buat cut sections, yang hujung sekali kan, beam yang hujung sekali dia adalah L-beam. Mana-mana beam yang dekat internals ni dia akan jadi T-beam sebab dia ada portion slab at both side. L-beam only have a portion one slab, okay, only at one side here. Okay, flange beam also can be determined as a singles and also as a double. Sama juga dengan T-section. Dia boleh jadi singular which is just provide AS, and once the beam have to carry high load, so it can be designed to be a double section, double reinforcement that have a AS and also AS prime. Right, so this is the flange here, okay, the flange beam here, which is the top one, we call it as a flange. This is the flange, okay, which is combinations of slab and also the beam here. Okay, combination of slab and also the beam. That is the flange, which as a part of the compressions area. So kalau web here, web yang bawah flange, okay, which is below the flange here. That's we can say that's which is it consists of the beams, okay, consists of the beam. So the top one is the flange, this is the flange, while the bottom of the flange, this is the web. So the web maksudnya the beams, okay, this is it normal width, dia punya lebar, biasalah lebar beams. But for the flange, it have its own effective flange width. We call it as a B effective. Dia punya lebar efektif untuk flange. Okay. Alright, so if you can see here, this is for the whole beam. Okay, for the whole beam here. What is meant by B effective here, effective width of the flange, which you can see the informations, the equations in sections 5, 3 to 1 in EC2. Please find out this page. So B effective here is actually based on the distance LO, okay, between point of zero moment as shown in this figure. So the beams here is support at this point, let's say I support this point and then this point, while this is hanging, okay, hangings region here, which is the end of here, it's free, there's no support at here. Okay, kalau for the first span here, which have a support here, so we will use these equations, which is LO is equal to 0.85 L1. L1 is actually the span for the first one, LY. The next span is the L2, the next, and so on, L3, L4. Okay, so the first span here, this is equation for the LO, distance for the LO, 0.85 L1. Then from the supports to this in between this support here, LO is equal to 0.15 L1 plus L2, both sides L1 plus L2. For internal span, okay, this is the first span. It doesn't matter right or left as long as the first span. While this is the internal span, tak kisahlah internal nombor satu ke nombor dua, as long dia dekat dalam. Internal span, you need to use LO is equal to 0.7 L2 according to its length of the spans here. So this one, if the beams is a hanging beam, right? Hanging beam, okay? Bahasa Melayu rasuk juluh, okay? So any cantilever beams ke kan, which is 0.15 L2 plus L3. So that means for the beam span, for the whole beam span, you need to identify which one the first span, which one the internal span, dan kalau ada cantilever beams here, so you need to use of these equations. So actually this LO distance is based between zero moment. So kalau you lihat this curve for the moment, this is zero, right? And then it's cross at the zero here, then cross at the zero here. So which is this length is actually is a LO. LO from the moment zero to this moment zero. LO at the support from this moment zero to this moment zero. LO for the internals actually is from this moment zero up to this moment zero dan seterusnya. So how to know this LO? Okay, how to know of this distance from zero moment to zero moment? By using of this equation 0.85 for first or end of the span, for the internal 0.7, for the cantilever beam is 0.15 here. Okay, so kalau macam ni, mana satu ni ada brackets, right? Okay, so please refer these sections. Okay, which one is the correct one? Is it 0.15 L2 plus L3 or have a bracket here? Can you understand me? Faham tak korang? Tak ada suara lah.
Faham.
Ada pun suara kan. Okay, so then this is equation of B effective. Okay, so if you look at in this equation, ada LO kat sini. So that's why you need to determine the LO first. Okay, this is equation for B effective. So you need to know what's the LO first, baru you boleh substitute in this B effective equations. So B effective equation is equal to the total of B effective I, which is I, it can be 1, it can be 2, right? Total of it plus BW. What is BW? Is the width of the web here. What you want to determine here is the width of the flange. Okay, so this is BW. That means you also need to know what's the BW, you need to know what's the LO, and then also what's the BI here. Okay. Alright, so B effective I here, B effective I is equal to 0.2 BI plus 0.1 LO, which is L distance. Okay, is it the first or internal or cantilever? Okay, this is what it's mean by B effective. Okay, what is mean by B effective, which is this is for example, this is the flange beam, T beam, which is normally can be found for the internal beam. Okay, for the internal beams here, B effective it means the length for the beam here, the length for the T beam. So BW is the width for the web. B effective I, it means B effective at both sides. Okay, so kalau T-beam ada B effective 1, ada B effective 2. Alright, then also have a B1, B2, which is B1, B2, it's from the span. That means B here is a half span. Okay, daripada center to this center. So you need to divide by 2. So you need to divide by 2. You get half of it, and then you have to minus half of the BW. So this is the length, the clearance actually. B1 is from the center span to the surface of the beam. B2 also, you need to divide this span by 2, and then from the surface of the beam to the center span is a B2. Okay, same goes to other beam. Kalau L beam, okay, kalau L beam, so ni ada slab lain lah. So ni L beam. Sama juga, ni adalah B effective. So, but because of L beam, it only have BI, it only have one side, right? It only have one side here, which is, this is which is B effective 1, because only have one side. This still BW, this still BW. So from this surface, from this concrete surface to the half of the spans, this is B1. Okay, because of L beam it only have one side. Sebabkan T beam it have two side here, which is B1 and B2. So that means there will be B effective 1 is equal to 0.2 B1 plus 0.1 LO. Then we have another one, which is B effective 2 is equal to 0.2 B2 plus 0.1 L1 kalau T-beam. Then total of B effective 1 plus total plus B effective 2, ni lah maksudnya total of all the B effective 1 and 2. Then you need to plus with the BW in order to know what the B effective of the T beam. Kalau L beam here only have a 1 B effective 1 plus BW, that is equal to the B effective for the L beam. Okay, so you need to understand this carefully. Okay, especially for the flange. So there will be a the question for the flange. Senang je, logik je. Kalau test tak keluar flange, of course final mesti keluar flange. Tu which is we want to cover everything, so you need to understand this one. In the project also you will have to design for the flange beam also. Normally beam will support the slabs, right? So kalau tak ada slab, selalunya on the at the roof level. Okay. Alright, so we go straight to the example here, which is if you look at here, this is the first the first view for the beams, right? Then we have another one. We need to see the cross section of the beam. That means you kena letak mata you dekat dua directions. Okay, you have to positions. Put your eyes at two directions, two different positions. Okay, look at of this example carefully. You need to determine the effective flange width here. That means B effective, okay, for the beam B1, 2, 3. Okay, so this is how we do the label for the beam. It should be correct label. Beam B in range 1 to grid line 3. So this is the what it's the need for this questions here. You need to determine the B effective for this beam. So don't look at other beam. Just focus for this beam B from grid line 1 to 3 here. So this is the first eye, the first position for your eyes. You need to look at from the sides that can see the whole length of the beam here. Okay, which is this is continuous beam from grid line 1 to up to 3. Sekejap screen. Alright, so letak dia punya mata yang nampak keseluruhan panjang beam tu. So from these directions, so if I sketch it, so it will be like this. Okay, so this beam B, line 1 to 3, you akan nampak whole length, okay, keseluruhan beam B. Tak nampak lagi dia rectangle sections ke, dia flange beam ke, tak nampak lagi. Just nampak panjang beam tersebut. Okay, so grid line 1, grid line 2, grid line 3 with the length of 3 meter and 4.5 meter. That means you will have two span from 1 to 2, span from 2 to 3. This is the first view, the first draft. Okay, then the second position for your eyes, it should be at these directions. Okay, you tengok beam tu daripada depan. Ni you tengok beam daripada tepi, nampak all the whole length. Then the first position for your eyes, it should be directly in front of the beam here. So kalau lihat dari sini, I try change the color. Here. So kalau lihat dari sini, you akan nampak dia punya cut section. So that means if I cut these sections, okay, you see all the sections of the beam. The first one will be the beam here for the beam A, and then you will see the slabs, right? And then the beam here, and then the slab, and another beam here. Okay, so you have L beam, okay, at the corner, and then internal here as a T-beam. You nak design beam B kan? So just focus the shapes for this beam B, which is the cross section. Here is a flange beam for the as a T-beam. So this will be your beams to be designed. So tak payah nak tengok beam A dia L beam, beam C L beam memang, tapi you need to design T beams, T section for the beam B. Okay, so that means this all of the beam B here will be T sections. Okay, semua ni beam B ni adalah for the whole length here is a T section. So if I make it in a horizontals here, this is how your eyes will see for the second positions. Okay, you nampak dari depan, which is this is the beam B. So daripada sini you need to know what's the B effective for this beam B. Right, so what's the B1, BW for the beam B? So that means there will be a portions, okay, along of the beam here, which is the flange portions. Tak tahu sampai mana, which is this is what it mean by the B effective. Okay, so this is all the B effective for the flange beam. Any questions before I proceed?
Tak ada, doktor.
Okay. Alright, so this is the first view, right? From your first eye positions, which is from the first positions here, first eye view here, you can come out with LO. Okay, what the first spans equations for the LO is a 0.85. This one also the first span, right? The first span from the right side, the first span from the left side. Tak ada internal span kat sini sebab dia ada dua span saja. Kalau ada tiga, so this is LO dia adalah 0.85. This is the first span. This one also the first span, which is LO 0.85. But this one is the internal, right? So you kena guna equation internal 0.75. Betul tak 0.75? Ada lupa. 0.7. Kan, tak ada cantilever. So nampak tak? Because of this only have two span. So the first 1 to 2 also the first span from the left side. 2 to 3 span here also the first span from the right side. So both of it will use LO is equal to 0.85. 0.85 L This is the L here. L2 dia punya span lah. Okay, dia punya span ni adalah 3000. So you just calculate lah what's the L distance, LO distance for 1 to 2 and then from 2 to 3 which is 3825. While this is for the support. Okay. Alright, so settle for the first view. Then next, this is the second eye view, right? Okay, which is you will see all these cross sections, which you just need to focus for the beam B. Okay, that produce these T sections. So determine the B effective for this one here. Okay, if you can see, this is the equation for B effective. Baru nak tahu B effective ni, which is according to this equation. B effective I, this one, which consists of BI and also LO. LO tadi dah dapat daripada first view. Okay, LO2550, LO3825 for span 2 to 3. So how to determine the B effective I? So you need to obtain from the second view. Okay, so you kena apa ni, divide by 2. Okay, 2500 dia punya span ni kalau lihat balik. So daripada center ke center 2500, you have to minus half of the BW, half of the BW here, which is, this is the size it's given, which is 200, dia punya width dia. So 2500 minus 100, half of this beam minus 100 of this beam. So that's why you will get 2300. 2300 ni, okay, divide by 2. You will get B1. B1 is from center of the span to the surface. So B1 1150. And then B2 is 1900, which is this 4000 minus half of this width minus half of this width. You will get the clearance, right? From surface of beam to the surface of beams. So this is clearance space, which is from surface to surface of the beams here. You need divide by 2. You'll get from the surface of beam to the center of the span, which is 1900 here. This is BI for 1, BI for B2 here. All right. Okay, so by using of this equation, you will get two side, right? Because T section have a two side. Side for B1, side for B2. So just replace the value here, 0.2 B1, which is 1150, plus 0.1 LO. So kalau tak nak confuse, I suggest you for span 1 to 2, LO dia adalah 2550. So look at back this view here. LO from span 1 to 2 is a 2550. LO for span 2 to 3 is a 3825. So that means there will be two spans calculation. Spans be effective for 1 to 2 by using LO 2550, and then we have another one from span 2 to 3 by using LO 3825. Clear So you kena buat noted kat sini, tak nak confuse. Alright. So that means all of this B effective will use this LO. Okay. For span 1 to 2. Just repeat equation, you will get 485. You need to compare. Okay, it limitation 0.2 LO, just substitute the value of LO. So and then B1 here, okay, which is 1150. Okay, same goes for another side, the second side for B2, which is 0.2 multiples with the 1900, it's B2, plus 0.1, then dia punya LO 2550. Then you make a comparison with the limitations. So mana yang follow the limit, you can use that value, which is 485. But this one is more, right? It should be less or equal than 0.2. So if the value more than it, so that's mean you need to use 510. Okay, you need to use the limits value here, which is 510. So in order to compile all the B effective 1 and B effective 2, which is this is the completion, the total of both sides. So 485 and 510. Okay, plus dengan BW. BW ni lah. Okay, the width of the web beam. So B effective for the beam span 1 to 2 adalah 1195. Okay, 1195. So kalau I lukis balik kat sini, padam bagi faham. Okay, flange for this beam. So this is the beams, right? So that's B, dia punya B effective adalah 1195. Okay, this B effective, oh my god. This B effective is 1195 mm. Ni adalah lebar flange untuk span 1 hingga 2. So ni adalah lebar dia. Katalah, okay, kalau nampak di atas, inilah lebar dia 1195. It's B effective up to grid line 2. Okay, so then what pula grid line 2 to 3? So we have another span, right? 2 to 3 that use LO3825. Do the same procedure. Okay, by using LO3825, di B1, this one B2, right? Kalau lihat kat sini, saya rasa ada silap value ni. Which is, that's mean you need to compare, right? Compare from center to center. Center span to center span, which is center here to center here. It should be include BW, right? So 1150 plus BW plus B2, which is 1900. It should be plus another 200. So it should be 3250. Kan dari center span ke center span mestilah termasuk BW ni, dia tak plus BW kat sini. So that means this is 3250, but still less than 3250. This one ni correct, but this one dia tak masukkan plus BW, which is to make corrections, okay, on your slide. So from span 2 to 3, the same procedure, the same equation, you will get B effective for span 2 to 3 is a 1575.5. So that's mean kalau you tengok view dari atas ni, ni 1195 kan, tapi bila untuk span 2 to 3, dia punya flange width dia lebih besar sedikit. So it's still T sections, but the B effective cover more than span 1 to 2. So dia cover besar sikit, which is 15, berapa tadi? 1575. 1575. So nampak tak? Kenapa tak sama sepanjang ni? Sebab span dia pun tak sama. Kan? Dia punya span pun tak sama. Kalau span dia sama, ini 3000, ni 3000, ni sama 2500, ni pun sama 2500. Dapatlah sama saja span 1 up to 3 because of different spans here. So dia punya coverage, okay, for the T beam here, it will be different. So that means you have to design these two size of the beam section. So that means for this beam B akan ada dua section. Section for span 1 to 2 with the B effective 1195, yang lain samalah. The difference is the B effective. And then span for 2 to 3, dia punya B effective a bit bigger, more bigger because of different spans. Okay, so it becomes 1575.5. So both of these is the T sections at the same beam, grid lines, which a beam B, but what different is it B effective. So these both beams can be singular or can be doubles. Depends the moment that apply on it. Is it these sections can resist or not for the beams, or might be need another help, another additional reinforcement for the compressions reinforcement. So that means either design as a singular or design as a double reinforcements. So that means there will be a checking comparison here. Is that beam have to design as a single or might be have to design as a double? All right. So um, uh, what we want to know here, is it singles or doubles? For the flange beam, it depends where the neutral axis lies. Kat mana position neutral axis? Because we have a flange section and also we have a web section. So in the case of neutral axis lies in flange, okay? So neutral axis tu dekat flange. Ataupun neutral axis lies at the webs here. So there are three cases here. The first case for the neutral axis lies in flange. Once the moment, design's moment, less than MF. MF is the moment for that sections. According to the grade of concrete, according to the size of that flange, which is MF. Kalau apa ni, rectangles tadi, kita compare dengan M balance kan, kita panggil dia M balance, sama je M balance. That means according to the concrete grade, according to the size of the beam. Flange also, so what is the capacity according to the that sections here, then you need to compare with the load, with the moment that applied, okay, that applied on the beams. So the second and third case, which where the neutral axis lies in web here. Okay, dia ada dua case kat sini. Okay, so this case, once M less than M flange. For the case of neutral axis lies in web, it have two cases here. So M more than MF, both sama once M more than M flange, tapi you need to compare with another one that is M balance. If moment more than M flange but less than M balance, you need to design just a AS here. Yang this one, once moment less than M flange, you have to design just tensions reinforcement, just a singular. But for this neutral axis lies in where it have two conditions. Less than moment balance, just design as a singular. Okay, same goes to the rectangle, same goes to the first beam here. But once moments more than M balance, you have to provide the AS and also AS prime. That means compressions, reinforcements. Okay, so kalau more than MF, you kena checking lagi satu, M balance. Sama ada dia kurang atau lebih dengan M balance. Sama ada neutral axis lies in web tapi just design as a singular, ataupun neutral axis lies in web but you need to design with the compression reinforcement as a doubles reinforcement. Okay, so this is how the block diagram looks like once the neutral axis lies in flange here. So HF is the thickness for the flange. Okay, so this is B effective for the flange, and then this is VW for the flange. Same goes for the D here from the top surface to the centroid of the AS. Okay, will be the D effective here. Tak ada D prime kat sini sebab tak ada compressions reinforcement, only D effective for the tensions reinforcement. So this concrete diagram here, this concrete force here is a 0.8 x. Dia lawi sikit ni, boleh betulkan. Which is the thickness for the concrete diagrams here is a 0.8 here. Okay. Okay, so same because of there's no reinforcement here, just consider for FCC for the concrete, the same concepts, and also FST for the reinforcement, for the tension reinforcement, and then we have the Zs and everything. Summer concepts here, okay, which is you have to come up with the moment, determine the moment in order to develop the equations, right? What's the moment at this point, which is FCC multiply with the Z here, you'll get the moment resistance for these T-beam sections. Okay, and then you can make equilibrium for all the forces. FST is equal to FCC and so on. Okay, so from all the equations, okay, from all the equations, you will get this MF. This is M for the flange, whereas the moment that you will compare with the designs moment, which is 0.67 FCK, B effective, HF, and then you have to multiply with the D minus HF divided by 2. Okay, so as long as you understand to determine B effective, and then what is HF is the thickness of the flange, right? This is HF, this is B effective. Okay, remember how to get the B effective. It should be eyes along the bar or the beams, and another position of I is according to the sections. Okay, then you can calculate the M flange here. So you need to compare with the moments. Okay, with the moments. If less than M flange, so neutral axis lies in flange. So that means the neutral axis lies in a flange here. Okay, so this is the X here. So that means you just need to design as a rectangular singly reinforced beam. So just single reinforcement, just provide AS. So this is the equation for the S, which is just use the equation that is for the rectangle singles single reinforcement. Okay, guna sama saja equation. So this is just elaborate lagi lah what is Z is. Okay, Z is equal D minus 0.4 X. So this is the examples here. Okay, for the this T beam. Okay, dia tunjuk sini AS but it didn't give any value. So what's the numbers of reinforcement here? That means you need to determine the area and number of reinforcements required. So kalau tengok macam ni dia dah bagi siap-siap AS kat bawah ni. So dah tentu dia punya M will be less than M flange. Okay, so what you need to understand here, M here, which is the design moment, the real moment that this beam should be carried out, which is the design moment is equal to 250. So nampak macam senang kan, semua soalan dah bagi design moment. Okay, sebab nama pun contoh. Tapi the real procedure is you need to find out from the beginning. Kalau moment you dapat salah ni daripada awal-awal lagi, so from the GK, QK, right? From this one, you have to come up with the moment. This is what is meant by moment 250 from this analysis. Either just using equations or using tables or using distribution method envelopes. So this is what it means. This is what the value come from 250. Because of the example, just give you senang-senang bagi je design moment. Tapi dalam design yang sebenarnya, dalam question soalan nanti, finals nanti, you have to come up from the beginnings. Sama juga project. You kena cari dari awal lagi the loading of GK, the loading of QK, then come up with the analysis for the moment here. Then barulah boleh guna to compare with the M flange, to compare with the M balance. Then baru you boleh provide everything. Salah mula-mula lagi, salah lah you punya AS provide. Okay. Alright, so you have to calculate the MF because you want to know is it singular or double reinforcements, right? So calculate for the MF and then compare with the M. M tu dah bagi design moment adalah 250, which is less than the MF. That means the neutral axis lies in flange compression. Reinforcement is not required. Ni titik ni. Okay, so that means compression reinforcement is not required. Just designed as a singular beam. So according to the diagrams, block diagram equation, you can determine from the quadratic equations. This is the same procedure for the rectangle singular beams. Okay, this is the same procedure that you will apply. Okay, consider you need to determine the X, right? Because you need to check in X divided by D. Right, so do the checking. So daripada checking, it will shows either the steel achieve the yield strength or not, achieve the design strength or not. So kalau achieve, you can proceed. That means you control the beams to be under reinforced to ensure that the steel achieve dia punya yield strength first before the failure. Okay, then calculate for the AS. Terus dapatkan dia punya AS. Dalam AS ada Z here. So that's why you need to determine the Z here. What is the Z? This is the distance, right? For the Z here, which is equal to D minus 0.4 X here. Okay, so dapat AS required 1895. Then you can provide any numbers, any diameter, as long as AS provide is more or equal to 1895. This is the nearest one, the best one. Okay, bilangan reinforcement pun just nice. janganlah banyak-banyak. So size pun tak adalah over sangat, tak adalah besar sangat. So just nice, nanti at side apa ni Pak Indon boleh susun reinforcement tu. So susun cantik 4H25, size pun okey, taklah besar sangat. So nanti Pak Indon tanya, wah siapa yang design ni? Kan engineer dari UTHM. Gitu. Alright, so then we have the second conditions here. Once you punya design moment M more than NF, more than MF, which is the neutral axis lies in web. But at the same time, you need also to check with the M balance. Is it less than M balance or more than the M balance? So in this case, once the neutral axis lies in web, macam mana you all nak continue ke nak rehat kejap ke dah meleleh-leleh kat telinga tu? Nak stop kejap ke nak sambung? Ngajar syok je, tak tahu korang macam mana. Cepat. Decision. Engineer kena buat decision nak sambung lecture ataupun stop kejap bagi tak meleleh kat telinga tu.
Ya, kejap tu.
Okay, alright. So rehat sampai 11.30 Okay. Okay. Okay, we continue, all right? So next we have seconds conditions. So look at X, what I've do some sketch before this. So this one settle, which is once moment less than moment flange here. Okay, so that means you just need to provide the AS. Okay, then we go for the second conditions here. Okay, once the second condition, this is the first condition. For the second condition here, it have two situations, okay, which is once moment more than mf, but at the same time you need to check either that moments less than moment balance or more than the moments balance. But what the same thing is, the neutral axis will lies in the web here. Okay, once the neutral axis lies in the flange for the first situations, okay, for the first condition, neutral axis lies in the web. So that means it only have a FCC at the compressions area. Okay, this is only FCC for the compressions area. So the bottom here, okay, the bottom one here is the tensions area. So which the tension will be supported by the FSD, by the steel reinforcement. But for the second case here, okay, once the moment more than MF, that means the neutral axis will lies in the web. Will lies in the web here. This is the neutral axis. Okay. So once it lies in the web, that means the concrete will be split into two. Okay. There will be a concrete at webs, there will be a concrete at flange. Okay, that means there are two area. Ada area flange, ada juga termasuk kat sini area web. Nampak tak? Kalau yang first tadi, for the whole area, the top one is from the flange. So that's why the forces will be considered as a FCC. Okay, but the second condition here, once the neutral axis at the web here, the compressions area consists of two area for the web and area for the flange. Okay, ni concrete dekat flange, ni concrete dekat web. So that's why for the forces, there will be a FCC1 for the FCC1 for the first area here, okay, with combinations of flange and web. And the second area is a concrete of flange. Okay, this is the second area for the concrete of flange. All right, so that means there will be two forces at the concrete, which is two forces compressions, two forces concrete at the compressions, which is FCC1 and FCC2. Then AS still the same, which only consists of FST for the steel in tension. So kalau less than imbalance, it's still designed as a singular. It's still designed only tensions, reinforcements. Tapi FCC ada dua, FCC1 and FCC2. FCC1 for the web and then FCC2 for the flange. Both of it still concrete. Okay, still concrete in compressions. Okay, so that means there will be two forces here. The concepts, basics, it's still the same. FCC1, FCC2, and FSC. That means there will be a three internal force. So there will be Z1 and also Z2. Kalau Z1, so Z1 it's at the center. Okay, Z1 at the center of the concrete. At the center, which you need to divide this 0.8x here, which is Z1 is equal to D minus 0.4 X. Kalau Z2, it's half from the HF because of this flange, right? So you need to divide by 2 this HF. So that means Z2 is D minus 0.5 HF. So again, for moment resistance, bring all the force, calculates the moment, all the moment at this point here. So that means FCC1 you need to multiply with the Z1, and then FCC2 multiply with the Z2 in order to come out with these kinds of equations here for the moment resistance. Okay, kalau ada soalan bagi T sections, right? Okay, so what's the moment resistance for this section? Ni lah equation dia, nak cari berapa moment resistance for this sections according dia punya sizings, dimensions and everything. Okay. Alright, so this is the second checking here, which is you need to do the checking also with the imbalance. Okay, so we know the limit here, which is x is 0.45d. Okay, which is x divided by d. It should be less than 0.45 here. So from these equations, okay, you need to replace all the xk to be 0.45d in the equations here. So this is the simplifications, which is the simplifications of the equation of imbalance, which is you will need use of these equations, okay, to compare the moments. Is it less or more than the M balance? Okay, nampak kat sini balik. You kena buat checking dengan M balance juga kan. Okay, okay, checking M with the MF just to know, is it the neutral axis lies in the web, in the flange, ataupun neutral axis lies in the web here. So kalau lies in the webs, okay, once M more than MF, right? So that's mean the neutral axis lies in the web. So at the same time, you need to do the checking with the M balance in order to know if the compression reinforcement should be provided or not. Okay, so the first thing you need, the second thing, that's mean you need to do the checking with the M balance here, which is beta F here. Okay, beta F here is from these equations. So beta F is from this equation. So you kena masukkan lah, senang je ni equation ni, BW, dia punya B, kan, B effective dia, HF, and then dia punya D effective here. Okay, so masukkan beta F, you get the value of M balance here. Alright, so the last type is once the M more than the M balance. This one is still the same. Once M more than MF, the neutral axis lies in the web. At the same time, you need to do checking with the M balance here. So use these equations, okay, of AS here. Okay, so once X is the limitations, Alright, and then samalah juga ni dengan moments ni. Dia punya AS ni sama je macam tadi. Okay, so uh, this is the example. Kalau tengok example lagi faham. Okay, diberi kat sini, dia punya design moment adalah 670. So everything's stated here. Okay, all the size, flange thickness, BW, D effective here. So the question is, determine the area and number of reinforcement required. This T flange can be singular, can be double. Okay, can be singular or also can be double, which consists of AS prime. And another one thing here, you need to identify its kena identify dia punya neutral axis. Neutral axis. Sama ada neutral axis in the flange or neutral axis in the web. Kalau in the flange, so dia punya shear force diagram only have FCC. Kalau in the web here, there will be two forces of compressions, right? So which is there will be FCC1, which is at the center of the diagrams of the block here, and another one, the center of the H thickness, HF thickness, there will be a FCC2. Okay, because of the concrete, it's be two areas. Okay, kalau lies in web, there will be two areas. Okay, this is concrete for the flange, solid for the flange, while this one is a combination for the web here. Okay, dia punya maksudnya dia punya B dia akan just for the BW here. So that means combination of concrete in flange and concrete in web here. Okay, so that's why there will be a FCC1 and FCC2 once the neutral axis lies in the web here. Okay, so you need to determine the area and number of reinforcement. So you need to do the checkings, right, with the MF. Is it M less than MF or M more than MF here? Okay, kalau less, neutral axis lies in the flange. Kalau more, neutral axis lies in the web. So it shows here that M more than MF. So M dia bagi berapa tadi? 670 kan? Okey, 670. Dah duk kira MF ni. Okay, by using of this equation, it shows that 665, which is less than M here. So that means this becomes neutral axis lies in web. Okay, so since M more than MF, neutral axis lies in web, you need to do the second checking with the M balance, right? We have a M balance. So is it less than M balance or more than the M balance? So this is the equation for the M balance, which is beta F. This is a beta F ni. This is beta F, which is this one. Okay, you need to calculate first what's the value for the beta F and then replace in the equation. It shows here that the M balance is 682 kilonewtons meter, which is M is less than M balance, the first one here. Okay, M is a 670, M balance is a 682. So that means compression still not required. So kalau M balance ni just AS. Just AS. But you cannot use the same equation for singular rectangles. It have its own equation for the AS. Susah betul. Kalau dapat M more than M balance, okay, you need to provide AS prime and also AS. Tapi in this case, M is less than M balance. Okay, for the neutral axis lies in the web. So compression reinforcement is not required. You just use of these equations. Okay, tak boleh guna yang rectangle. AS which is AS is equal to M divide tak ingat lah 0.87 FYZ ni tak boleh guna lah. This is for the first case that is lies in flange kan, which is singular can just follow equation of rectangles, boleh guna. Tapi kalau once lies in web but just need to provide AS, so you need to use these AS equations. Okay, once the neutral axis lies in the web here, so blah blah blah, dapat AS provided 64338 H32, banyak kan. So flange should be bigger size here. So 8, susunlah mungkin 1, 2, 3, 4, 7, 8. Bila susun tu it should be apa ni, equilibrium, mesti dia punya seimbang lah, mirror, it should be mirror. Okay, it should be mirror. Alright, so the seconds still lies in the web, but dia punya moment more than the M balance, more than the M balance here. So that's mean you need to provide the still in compression. So you'll have a AS prime here. Okay, you will have a AS prime. Once you have a AS prime, bertambah lagi dia punya forces. Tadi because of concretes at area 1 and area 2, you will have FCC1, FCC2. Then we have to provide the compression reinforcement. So tambah lagi satu forces, force of steel in compression. You nampak tak? Once it becomes double reinforcement, you punya design pun double. You punya procedure pun makin panjang. So that's why kalau dulu saya project kan, bila buat design beam, bila calculates all the load, sekali dapat moment which is less than M balance, so macam gembira. Sebab simple je lah design, you kena cari AS je. Tapi bila calculates according to the loading, sekali dapat moment lebih daripada M balance. Kena tambah pula compression reinforcement. So that mean you punya calculation tu bertambah lah. So sama juga macam inilah. Okay. That mean you punya kiraan moment tu penting. Adakah betul moment tu tinggi? Adakah moment tu cukup? Sama ada singles or double reinforcement. Okay, ada juga dalam soalan. Soalan tu loading dia taklah besar mana, tapi bila you all calculate, you punya besar tu sampai you dapat a double reinforcement, you need to provide the AS prime. Sedangkan dalam skema jawapan, you just need to provide the tension reinforcement, just need to design as a single reinforcement. Dah rugi masa kat situ kan, disebabkan you salah kira loading, salah kira moment. Okay. So bila ada three forces here, so that's mean you will have these three Z, Z1, Z2, Z3. So bring all the moments here in order to calculate the moment resistance. So FCC1 darab dengan Z1, FCC2 Z2, FSC darab dengan Z3 here. So you will have all of these forces, including the forces for the tensions, reinforcement, which is FST. Ni FST. Dah 4 forces semua. So this is all the internal forces, which all the Z here, and then moment resistance for all the three forces. If you calculate the moment resistance at this point here. Okay, so then you will need to provide the AS prime. So you can just use of these equations here. So that means all of this equation you don't have to remember. So you don't have to remember. Dalam BS pun ada. Even kalau face to face pun you tak perlu hafal lah. So as long as you understand the block diagrams and then also included in the mungkin appendix kita letakkan ke, so tak payahlah nak duk hafal. Bila online lagilah korang tak hafal kan. Cakap jangan tengok buku, you all tengok je buku. Siapa yang nampak kan, di sini yang tahu. Okay, dah sakit tekak dah ni. Ada soalan? Okay, AS. So AS prime pun kena provide. Of course, tensions, reinforcement pun kena provide. Okay, just using of all of this equation. Yang penting masa kira BF tu tadi betul ke tak betul. Tu je. Masa calculate AS tu betul, AS prime tu betul ke tak betul. Awal-awal dah salah, yang lain semua follow salah. Semua follow value semua salah kan, dari awal dah salah. Okay, so make sure be careful once you do the calculations. Okay, so dia akan melibatkan, rosakkan calculation yang seterusnya. Habis. Okay, settle for French here. You need to understand how to determine the B effective first. So once you dah complete, okay, so that means you have already complete for this flange beam. That means you can proceed your project. Just semalam saya cakap tak boleh lagi proceed flange, buat dulu roof kan. So because of rectangle sections, but because you already complete flange, so that means you can start your project. Okay, you just for this subject just design the beam. Ada tanya nak design kolom tak? You all ada belajar kolom ke untuk subjek ni? Tak ada kan? Beam belum start buat lagi kan? Duk tanya kolom pula, duk tanya slab pula. No, you all mesti dah maklum for this subject, this project, we just focus to design the beam, okay, for rectangles beam and also for the flange beam. Alright, so kalau lihat dalam author ada summary design formula. It shows the summary. Sebelum ni pun saya ada masukkan dalam group kan, telegrams. Also the summary. Okay, also the summary. This one another one from the author system. Okay, which is this is a other method kalau you guna K here. So if you make a comparison with the K, sama juga K dengan K balance. So this is equation for the K, which is M for the moment divided by B to the power of 2 FCK here, and then compare with the K balance. So K balance is equal to this coefficient, and then ada delta kat sini. Delta here is actually is the ratio between the redistribution, after redistributions, before redistributions, which is the moment. Kan bila momen asal sebelum buat redistribution mungkin hundreds kilonewton meter. Then kemudian buat redistribution, remember we can do the redistribution about 20% kan, nak reduce the numbers of reinforcement, the congested area of the reinforcement, especially at the intersections of the beams. So after 20% let's say redistribution, dia punya moment pun berkurang kan. Mungkin tadi 100 dah jadi 80 kilonewton meter. So make a ratio 80 plus 100. Berapa actually you punya delta here? Kalau ada redistributions. Kalau tak ada, so maksudnya after sama 100, sebelum sama 100, maksudnya data awak ni satu je lah. So kalau data satu, masukkan je lah satu. Nilai delta ni 1 minus 0.44 minus 0.116 in bracket 1 minus 0.44. If not mention any redistribution, that is how to do to analyze the K balance here. Then you make a comparison K and K balance. So kalau K less than K balance, compression reinforcement is not required. You nak guna kaedah ni boleh ataupun kaedah moment tadi, M less than M balance. This one if use K dan K balance. Kalau dulu saya belajar, saya suka guna ni. Saya suka guna K ni kan, sebab saya rasa macam lagi senang. Terus calculate for the Z here. This is equation for the K, for the Z, which is in the equation have a K here. So K is from K is equal to M divided by B to the power of 2 FCK here. Okay. Sebenarnya sama je, moment sama dengan K B to the power of 2 FCK. K tu apa? Kan? Which is 0.167. Sama je. Ni this other way. This another way here. So why you calculate the Z first? Because you want to substitute in equation of AS, which is compression reinforcement is not required. But once the K more than the K balance, you kena provide compression reinforcement. Once you have compression reinforcement, mestilah ada AS prime, mestilah ada D prime. So then you can do the checking D prime. Ini pun nanti the first one here pun you need to do the checkings, right? For the X divided by D. Kalau ada D prime, you need to do the checking. D prime divided by X should be less than 0.38. So ada dua conditions here, either more than 0.38 or less than 0.38 here. Okay. Alright, so AS, so this is all the equation for AS. So then this also summarize the design formula for the flange sections, okay, which is you need to do the comparison with the MF here. Calculate the MF first. So either neutral axis lies in the flange, right, ataupun neutral axis below the flange, that means neutral axis in the web. So ada dua condition. Ada dua condition, sama ada less than M balance or more than the M balance. Kalau condition less than M balance, compression reinforcement is not required, tapi you kena guna equation AS ni. Okay, kalau more than M balance, so this is all the equation that you need to use. Senang je guna equation everything, but you need to understand first lah which actually conditions of your beams, okay, either rectangles or flange. Kalau rectangle ke flange ke, sama ada single reinforcement or double reinforcement. Kalau flange, dia ada condition, neutral axis lies in the flange or neutral axis lies in the web. Okay, so dalam author juga ada masukkan contoh-contoh. Okay, contoh-contoh calculations lah. I will not go through. So I leave it to you. Kalau semua nak kena tunjuk in detail, so you tak ada effort nanti nak fahamkan. Kalau you dah tengok tak faham, tanya. Okay, so this is example for simply supported. So everything's data here. The first step, especially you need to extract all the data, all the relevance data. Kadang-kadang dia bagi data tu tak relevan pun saja je nak confusekan. So you need to pick up what's actually the information that you need to consider. Okay, so of course GK, QK kalau dia dah bagi directly, kalau tak you kena find out. Fire resistant, bila sebut fire je, exposure class ke, nak buat apa ni semua data ni, mesti you dah come out in your minds. Okay, so you mesti dah faham, oh ini nanti nak buat concrete cover kan, which is you need to have to fire resistant berapa hours, and then exposure nak tahu bonding, concrete cover and everything. So you kena refresh balik what you have learned before. Sebab this is the whole complete design from the beginnings until you come out with the AS that need to be provided. Okay, so the sizing. So kalau tak bagi size, you can do the assumptions. Macam project, I tak bagi pun size. You as the engineer, you can propose your size. Okay, tapi propose tu it should be logic lah. So common size, mungkin bar 120, and then links guna 8 mm, and all of this standard concrete strength steel. Alright. So this is another one thing that I want to highlight here. Actually, you can propose any size of the beam, but we as an engineer also have our aesthetic. Bukan engineer, bukan arkitek je ada aesthetic kan. Kita pun nak juga nampak kita punya tu structure cantik, nak juga nampak structure kita tu just nice dari jauh kan. Tak adalah orang tengok structure kita tu, takutnya kenapa kecil sangat kolam tu, kenapa tinggi sangat kolam tu, contoh. Okay, so this is might be you can use as a guideline here. Maksudnya it start from zero, you don't have any size here, but how to start it, which is you can use of this overall depth here. Overall depth here, which is H ni, which is L divided by 13. You can which is dia punya length berapa beam tu, divide by 13. Actually 13 ni it have a range actually. Okay, it have a range. It can be 14, 15, 16, but this is what is suggested by this which is I can say might be from Prof. Salih Yassin, Dr. Ramli, which is all of this we call it as a SIFU, our SIFU from UTM kan, all the notes for the design. So this is guidelines lah, which is L divided by 13. Ada juga orang buat L